first in our new webinar series for CanCore, which will profile all of the experts and researchers that are looking at carbon dioxide removal within this project. I'll do a brief introduction of the project, introduce our speakers, and then the rest of the time will be for Sasha and Jonathan to take it away. So the CanCore initiative is led by the University of Calgary, which is headquartered or located on the traditional territories of Treaty 7, comprising the Blackfoot Confederacy, that's the Siksika, Piikani, and Kainai Nations, the Stoney Nakoda Nations, Goodstoney, Chiniki, and Bearspaw First Nations, and the Tsuut'ina Nation. These lands are also home to the Otempeswak Métis governments, Districts 5 and 6. Personally, and our speakers are as well today, I'm joining from the ancestral territories of the nation's Treaty 6 here in Edmonton. And for those of you who need a reminder, next week, actually September 30th is the National Day for Truth and Reconciliation. And so I encourage all folks to look within their local areas for ways to get involved and deepen their engagement with Indigenous reconciliation. Maybe a quick intro about myself off the top. So my name is Carson Fong. I'm the program manager of carbon dioxide removal at the Pembina Institute, and Pembina is part of the CanCore initiative. This project aims to assess the potential of carbon dioxide removal technologies to meet Canada's 2050 net zero goal and to identify policy options that could enable sustainable, equitable, and rapid deployment of CDR in appropriate context. It's led by the University of Calgary, but also features experts from other institutions like Simon Fraser University, University of Toronto, and as you'll hear from today, the University of Alberta. And the coolest thing to me about CanCore is the breadth of disciplines that it encompasses. We have experts from political science to physics, law, engineering, geography, and so there's a real interdisciplinary approach taken to examining CDR in Canada. Overall, we have 25 faculty and staff involved, 30 graduate, postdoc, and summer students, and in-kind contributions from CanMet Energy. This is all made possible by support from Environment and Climate Change Canada, as well as Natural Resources Canada. And so what you're tuning into today is the first of many webinars coming in which we aim to share findings and insights with a wider audience to help advance the conversation of CDR in Canada. And so you'll want to make sure to stay to the end to hear about what's next in this series. So I'll introduce our speakers for today. Sasha Wilson is a professor in the Department of Earth and Atmospheric Sciences at the University of Alberta. Dr. Wilson is a mineralogist and biogeochemist with more than 20 years of experience in CO2 removal. He is currently the Canada Research Chair in Biogeochemistry of Sustainable Mineral Resources and the lead of the Environmental Economic Geology Lab at the University of Alberta. And Jonathan Spence is a PhD candidate in the Department of Earth and Atmospheric Sciences at the University of Alberta, working in Dr. Wilson's group. His research is focused on assessing the feasibility of enhanced rock weathering as a broad-scale mechanism of carbon dioxide removal. This involves assessing the CDR potential, co-benefits, and risks of different ERW feedstocks, as well as developing methods for assessing the progression of ERW and assessing the costs associated with the deployment of ERW across North America. I will now hand it over to Sasha.
Thanks very much, Carson. Before we get to the main event, which is Jonathan's talk, I wanted to give a brief introduction to the role of rocks in the carbon cycle. Next slide, please. Thanks. So rocks dissolving in rainwater regulate Earth's climate on the long term. So I've got an image here where we're looking at off the coast of British Columbia with Vancouver Island shown in the bottom right corner. And there's a big blue-green swirl of an algal bloom. So many marine microorganisms like algae will make calcium and magnesium carbonate-bearing shells. And that calcium and magnesium comes from rocks that are dissolved in rainwater. And that rainwater contains dissolved carbon dioxide from the air as well. So over time, when calcium magnesium carbonate minerals, these solid chemicals form in the ocean, we get some spectacular results. Next slide, please. Where thick rock units composed of that calcium and magnesium carbonate solids end up becoming so thick that they can make mountain ranges like the Canadian Rockies shown in this image here. So this is calcium magnesium carbonate rock, and most of the carbon on Earth is stored in these rocks, like limestone. So over time, CO2 is removed from the air by dissolving rocks to make new rocks that store it for a very long time. Next slide, please. So there are a few recipes that we can take away from how the Earth regulates climate so we can emulate them to speed up this process that removes CO2 from air and stores it in the ocean and eventually in rocks. So we can store carbon as carbonate alkalinity, so that's a dissolved form of CO2. And what we need is we need a basic compound, naturally occurring one, like basic minerals. So serpentine is an example of a magnesium silicate mineral that contains hydroxides. So it's a pretty strong base. When we react that with carbon dioxide dissolved in water, that makes carbonic acid, we get an acid-base neutralization reaction. And that turns the CO2 gas into a dissolved form, which is bicarbonate. We also get a bit of dissolved magnesium and silicic acid, which just stay in the ocean. So in this equation that I've written here with images of the reactants and products, the serpentine, this mineral that we find in rocks, for every 3 magnesium atoms we have in the serpentine, we can remove 6 CO2s from the atmosphere and store them in water. So storage as alkalinity, you get more bang for your buck than some other ways of storing carbon geologically, but it can be trickier to track. Next slide, please. We can also store carbon from the atmosphere in minerals, and this is ultimately where most of the carbon from the atmosphere is going to end up in the rock record, where it came from. So we've got the same basic mineral, a magnesium silicate mineral called serpentine, and reacts with carbon dioxide dissolved in water, which makes the acid carbonic acid. So it's that same kind of vinegar and baking soda reaction that we all learn about in school, but just with a naturally occurring rock and rainwater. When we make solid products, we produce hydrated silica. If you've ever bought electronics, there's always a little bag that says "do not eat." That's this stuff. It's also what precious opal jewelry is made out of. And we also get carbonate minerals. So this can be magnesium or calcium bonding on to carbonate and holding it in a solid rock. So this example here, magnesium carbonate mineral, is rock climbing chalk or gymnast's chalk. So what we make from this reaction by accelerating dissolution of rocks to draw CO2 out of the air is pretty benign products that we use every day. When we're storing CO2 in rocks instead of in water, we only get half as much CO2 pulled out of the air as we do when we store it in a dissolved form. But it's easier to see, and MRV, so monitoring can be a little easier because it's something you can hold and weigh in a closed system. Next slide, please. There are also applications of enhanced mineralization to the building industry. So our built environment, cement and concrete, is made from a product derived from limestone. So calcium carbonate, I've got an image of a nice naturally occurring calcium carbonate or calcite crystal on the left side. What we do to make cement is we roast that at very high temperatures to produce a base, calcium oxide, which is lime. And it releases carbon dioxide into the air. So that's one of the reasons built infrastructure is a big emitter of CO2. But we can reverse this reaction in our built environment. In the next slide, please. So if we take that lime that we're using to make walls and bricks, react it with CO2 in a way that speeds up this reaction, we can win back that CO2 and put it back into the same mineral that we originally formed, that we originally got the cement from. And so the calcium carbonate crystals look a little bit different than they originally did. They reemerge in the form of a brick. So this is another way that we can embed CO2 mineralization in some of our big industries. Next slide, please. So no matter how we remove CO2 from the atmosphere, it has to be stored using the Earth's geochemistry, or it'll get released again. So whether you're using bioenergy with carbon capture and storage, direct air capture with carbon capture and storage, or surface or deep earth mineralization strategies, everything's eventually going to go back into a mineral. And a lot of this is all about acid-base accounting. So just like reacting vinegar with baking soda, it's kind of the same principle, but it acts on the whole Earth system. So enhanced mineralization is really looking at mimicking the planet's natural acid-base chemistry, how rocks react with dissolved CO2 in rainwater. There are a bunch of different implementations, surficial implementations, which you can see in the top half of this diagram on the right side, and deep earth implementations. So what Jonathan is going to be talking more about today is a process called enhanced rock weathering, where rocks are crushed up and they're spread on farmers' fields. So this is essentially the same idea as liming, where farmers will use limestone, calcium carbonate, to mitigate acidity in soils and improve soil health. But instead, we're looking at using these silicate minerals that can sequester more CO2. We can also use enhanced mineralization in heavy industries, which are important in Canada, like cement and concrete production and mining. The materials produced by many mines are CO2 reactive. And then finally, we can couple any number of CO2 removal technologies with the underground injection of CO2 into magnesium and calcium rich rocks, where it will over time convert into solid forms of carbon. Next slide, please. So the scope of Cancor's work on enhanced mineralization is to focus on implementation in existing heavy industries, just big industries that mine and transport large amounts of rock in Canada and elsewhere as well. So with a focus on mining, the built environment with cement and concrete, and agriculture, which is the topic of Jonathan's talk today. We're looking to provide fill-in gaps in terms of rate data for CO2 drawdown with enhanced mineralization that are relevant to the Canadian climate to improve TEA and LCA, and looking for synergies between locations where CO2 reactive rocks are mined or quarried for these big industries to optimize enhanced mineralization. And so Jonathan will take it away with a talk about his geographic information systems approach to life cycle analysis and mineralization.
Excellent. Thanks for the intro, Sasha. Yeah, I think as Sasha mentioned, we're going to look at kind of the strategy for how to deploy enhanced rock weathering across North America, just in an economically and net emissions feasibly way. So let's we can go next slide. So just a little bit of background on kind of the way that enhanced rock weathering has been taking off recently. You can click a couple more times there, Carson. Yeah, one more as well. Perfect. So yeah, just kind of three examples of massive investments that have been going into enhanced rock weathering in North America, and it's not just in North America. There's deployments in India, there's deployments in Europe, but it is compared to other removal techniques, it is getting quite a bit of traction and getting quite a lot of investment. However, next slide. While it is growing rapidly with hundreds of millions of dollars invested, the price at which we're getting these investments is quite high. So it's currently between $370 to $375 per ton of CDR, which is not astronomical, but it's much higher than the kind of $100 target that has been set out for quite a while now to try and reach. So if we go next slide. Questions still remain. So there have been a lot of these sorts of studies that look at the feasibility of enhanced rock weathering, but generally they lack scope and granularity at the same time in terms of specific deployment ability for different areas. Next slide. So just a little kind of comparison for those deals we were looking at. So in that $375 region, it's quite high compared to other technologies. You see BECS down at the bottom there with, you know, $15 to $85. Even DAC up you know, second from the top from 135 to 345. So that kind of $375 range is quite high and you know, not quite as attractive from a dollar per ton of CO2 perspective. Next slide. So yeah, the question to ask is how can we deploy ERW for less money, essentially. Next slide. So the analysis I completed that we talked about today looks at kind of the cost and input emissions associated with deploying enhanced rock weathering across all of North America. It involves an assessment of the ERW potential of all the mines across North America, as well as kind of traditional LCA and TEA techniques, looking at the mining, grinding, and spreading components of ERW. And finally, it incorporates GIS network analysis to determine the costs and emissions associated with the actual transport component. Next slide. Excellent. So yeah, just kind of some of the input data we used. We identified a total of 152 mines or mining projects across North America that were potentially feasible for enhanced rock weathering. So of that, you're getting 114 basalt mines, 8 kimberlite mines, 24 serpentinite mines, and just 6 wollastonite mines, which is kind of expected due to the relative scarcity of wollastonite. These were all selected from USGS and the Mineralogical Association of Canada's database and filtered based on the lithology type as well as the commodity type. And one kind of important point to throw it right at the start is this is not considering deposit size. So especially with, you know, with the basalts and the serpentinites, it's unlikely that we're ever going to use up more rock than we have available. But with wollastonite and kimberlite, there is potential where if it does get deployed at broad scales, that you will actually run out of rock before you run out of CO2. So just a caveat there. Excellent. Yeah, so another obviously consideration for this analysis was the cropland area in North America. So using satellite imagery, we were able to identify about 223 million hectares of cropland. So an incredibly large playing field for enhanced rock weathering. Next slide. And just for a little more context, the LCA-TEA model we used involves multiple scenarios. So we're considering the use of diesel generators, grid electricity, or solar power at the mines to mine and grind the rocks, as well as both internal combustion engines and electrified transport trucks for the transport network. Next slide. Just a little look at kind of the input costs and emissions associated with the method. So these are based on the machinery, the labor, and localized energy costs, as well as localized emission factors for the grid electricity. And then the spreading costs are going to be calculated again based on machinery, labor, and localized diesel costs, with emissions being calculated just by the diesel usage rates. So if we look at kind of we look at the back one slide, sorry. Yeah, perfect. If we look at the kind of input emissions, you're getting this range from anywhere from about 7 kilograms of CO2 per ton of rock produced, all the way up to about 38 kilograms of CO2 per ton of rock produced. So not terrible input emissions, but that does obviously reduce the efficiency of your methodology, and then your input emissions for input costs for the mining and grinding is anywhere from about $13 to $30 per ton of rock produced. Next slide. Thanks. The final kind of input for this network analysis model is the transport network. So in total, we have about 700,000, just over 700,000 network components, which comprise roads, railways, and shipping routes, connecting all the various land masses of North America, and all the emissions calculated for the kind of transport across the network come from the Environment and Climate Change Canada's fuel life cycle model. And then, yeah, everything was input into an impedance model within a network analysis on ArcGIS Pro and Python. Next slide. Perfect. So this is just a look at one of the kind of preliminary kilograms per kilogram CO2 per ton of rock spreading maps. So you're obviously getting much lower emissions. This is specifically for serpentinite. You're getting much lower emissions when you're proximal to the serpentinite mines, or when you have access to localized railway or shipping routes. That severely reduces the costs, which is why you're seeing cost and emissions, which is why you're seeing the lower emissions in that kind of eastern North America and western Canada regions. And then you're getting this much higher emission band when you're getting into Mexico and Central America, again, due to less proximal mines and a less, I guess, dense transport network. Next slide. Thanks. So the next thing to consider is actually how much CO2 can we sequester or remove from the rocks that we're mining at these identified mines. And so the way we looked at this, we took an equation from out of a group at Trent, which Palo et al. 2021 paper, which is a great paper, and we looked at their methodology, which was for carbon mineralization, which looks at essentially the difference between the amount of cations and the amount of carbonate minerals, and from there you can determine your potential for carbon mineralization. But because we're considering alkalinity for enhanced rock weathering as opposed to remineralizing the rocks, we adjusted it slightly, looking also just at calcium and magnesium as opposed to all cations, because that's likely the minerals that are going to be readily weatherable. Next slide. So we did this in two ways. So we used this GeoRock database as much as possible. We wanted to get as localized geochemistry as possible. So from the GeoRock database, we're able to get thousands and thousands of geochemical data points across North America. And from there, we use the geochemistry data and input it into that modified equation if it was proximal enough to a given mine site. However, and next slide. Thank you. If it wasn't proximal, we did have baseline rocks. So we had a baseline basalt, serpentinite, kimberlite, and melastinite, which we analyzed ourselves in lab and then did the calculations for. Next slide. So this is kind of the end result, one of the scenarios at least, where we're looking at the actual cost per ton of CDR. So not the cost per ton of rock spread, but the actual cost a ton per ton of CDR. And you're getting this range anywhere from kind of $16 in the really proximal, ideally located areas, mainly in that kind of Midwest and Western Canada region, up to about $343 when you get into the more distal areas of the Central America. So it demonstrates quite a massive range in feasibility. That's 20 times from the lowest cost to the highest cost, and so it demonstrates the necessity of kind of planning and determining where you're going to deploy enhanced rock weathering, at least to start. Next slide. Just to kind of summarize the results, because it is a little difficult to kind of pinpoint just from a map, but it does demonstrate the same as you saw on that map, just that Canada and the United States clearly have quite lower costs than Mexico and Central America. And then, of course, the Caribbean is also quite low cost, and this is mainly due to the low costs and emissions associated with the transport of using shipping materials compared to transport trucks. And so you're getting anywhere in the range from, 60, so a mean cost of $67 for Canada to, up to a mean cost of $160 if you're deploying in Mexico. So it is incredibly variable depending on where you deploy. Next slide. Excellent. The final thing we did was just compare the kind of results of our assessment to actual regional costs of industrial carbon pricing. And so we looked at, the main carbon prices in North America are just within Canada and the US. And so within Canada, you actually do get quite a lot of feasible land, which is accessible for below our current industrial carbon price. Whereas, in the US, it's much less, between 0.1 and 0.6% of all farmland. However, when you look at just the $100 USD metric, it shoots up quite a bit, where you're getting, up to 98% feasibility in Canada, up to 88% feasibility in the US, and then, high feasibility in the Caribbean, and starting to see some feasibility in Mexico and Central America as well. So next slide. So this is not meant to be legible, but is just kind of an idea as to what the output of this analysis is. And essentially what it is we've broken North America down into each country and various jurisdictions, so province, territory, state, etc. And we've been able to give a mean, a low end and a high end cost per ton of CO2 for our optimized strategy, as well as our individual rock type strategies. So it's an incredible number of data points with kind of unmatched historically specificity. So it's a lot to read through, but it's quite interesting. And then yeah, just looking back at that initial graph we put up with the kind of costs of different CDR techniques, and looking at, we had these deals up at $375, and while that makes sense for lots of areas, that sort of price range, there are many areas that are accessible for quite a lot less than that, and it becomes much more competitive with other techniques when you do that optimization spatially. Next slide. And then just some key takeaways. ERW can be achieved for prices well below current offset deals. While the price does vary greatly by region and feedstock, there are areas in which the feasibility seems to be quite high, and it can be priced competitively with other CDR methods. Now, just a couple kind of final caveats to point out there is that there are two things I would really like to update the analysis for, and it's the consideration of MMRV or MRV techniques, because I know those can often be quite costly especially when trying to get your credits verified. And then also I'd like to consider some other CDR potential scenarios where we're not looking at just the geochemical potential, but more real-world realistic metrics. And so that's obviously going to shoot up prices in both cases. And then of course the other goal will be to expand this globally as computational power allows. So thanks. I think, yeah, this is just a sneak preview of kind of next steps, but gets a lot trickier when you get into more data sparse regions, but a fun challenge nonetheless. Excellent. Perfect.
Awesome. Thanks so much, Jonathan. And Sasha, maybe I'll also bring you back onto screen for questions. We've got a lot of time here to discuss some of these findings further. And so thanks so much for sharing the brief intro to mineralization and then the analysis, Jonathan, that you did. We've got a couple questions in the Q&A now. I'll invite the rest of the audience to jot down any questions you have. We can run through some of those, and I've got a couple written down too as you were going through your presentation. But the first one is from John. It's a question for you, Jonathan. Are all the mines used in your analysis existing? And do you know of any new mines for that are maybe on the horizon for any of those four materials you looked at?
Yeah, so I would say they're not all existing. So about 95% of them are existing operating mines or actually recently closed mines with large tailings piles, essentially. A couple of the Willastonite mines are just prospects, and as well as one of the serpentinite mines is just a prospect. So it's had all the kind of legwork laid for the kind of deposit size and geochemistry, but it's not actually been developed yet, and that's obviously dependent on economic factors for the materials, the commodities themselves. As for potential mines opening up, there definitely are there are new mines every year, certainly across Canada and the US. But it is often the data is a bit difficult just because the kind of mining companies, it's proprietary to their kind of cost models, and so it's a little more difficult to figure that out. But there certainly are mines starting up and prospect mines certainly across Canada, I believe across the US as well. But yeah, the data on them is not as easily accessible.
Cool. Awesome. Question from Allison. Could you elaborate on the primary contributing factors that you observed which bring down the cost per ton? So what are sort of the key variables that are driving that cost down?
So the kind of number one thing is proximity to a railway, essentially. If you're inland, or proximity to a shipping route on the coast, that your cost and emissions associated with transporting a ton of material in a truck is 10 times higher than that via railway, and about 15 times higher than that of a ship. So that's a huge cost cutter if you can deploy proximately to railways, which is generally advantageous because the Canadian railways were initially developed through all of our agricultural areas, so that's why Canadian costs are quite low. Is most of our arable land is relatively proximal to railways. In addition to that, the actual CDR potential is massive, right? So we kind of the scope of our analysis looked from anywhere from kind of 100 kilograms per ton of CO2 to sorry, per ton of rock, my apologies, weathered, to about 900 kilograms of CO2 per ton of rock weathered. And so when you have that nine times as much potential per ton of rock, it's going to be less than a ninth the costs associated. So that's a huge thing. And so properly characterizing any mine tailings or mine materials before you deploy them for enhanced rock weathering is incredibly important.
Maybe an extension on that question then, do you think, or I guess, what do you think about any potential technologies or process innovations that would have the biggest impact on bringing these costs down? Like, is it something within that mine tailing management, or is there something on the transportation side that you see potentially could have a huge influence?
I mean, I honestly, decarbonizing the economy in any sort of way is going to do that, because even if your trade-off from a gasoline truck to an electric truck is a slight increase in cost, which is what we found. We actually found you're getting a lower cost per ton of CDR because you don't have to account for nearly as much emissions coming out of your CDR potential as you transport it along the network. So it's going to be decarbonization. And then in terms of bringing down costs from a crediting perspective, it's going to be MRV costs. Those are astronomical right now, and they're the reason for these $375 per ton CDR costs. And so either determining a way to do that more efficiently or more cost effectively will be a massive improvement for that sort of TEA component.
Great. And maybe extending on that MRV topic, a question from Amanda. Do you know how you might plan to incorporate MRV cost into this model that you've built? Will you break it down by approaches? Do you have any thoughts on that yet?
Yeah, I mean, if you want to email me, Amanda, I'm happy to talk a little bit about that, because that's something I'm hoping for, people with feet on the ground a little bit for their input. I don't want to do this blindly. Yeah, I'm sure you know how to contact me, obviously. But the number one method I'm looking at right now is I believe it's, and if I get this name wrong, I'm very sorry. I think it's Cascade recently released a quite extensive MRV cost database. And so I'm trying to work through that to, it has quite a list of methods, but identifying the ones that are most readily deployed, I think I'll try and use those to start and go from there. But yeah, that'd be definitely input on that would be much appreciated.
Great. Yeah, I was just checking the attendee list of Ariel from Cascades here, but yeah, there's certainly some great work happening out of some of their modeling as well. All right. A question from Asim, either Sasha or Jonathan, up to you who wants to take it. Mineral carbonation is typically faster in presence of water, but what about dry stacked tailings? So maybe a bit of discussion about that difference and how that influenced the model.
Sure, I can speak to that one. An interesting thing, it's kind of counterintuitive that we see in tailing storage facilities, if you're looking at that kind of implementation of enhanced mineralization, is the ingress of CO2 from the air and dissolution into the water it actually slows the process down quite a lot. So it stalls the kinetics. There's an optimum water saturation that allows for the fastest possible CO2 mineralization. And that's somewhere between, I think, 30 and 60% water saturation in pore spaces. So dry stacking, if you can keep it damp, like damp stacking, that would be a lot faster for CO2 mineralization. And there's some nice papers from the 2010s by Harrison et al. And Asima et al. From UBC and Université Laval that cover the science on that. So dry stacking is ultimately probably your best bet for getting better CO2 mineralization in mining.
Interesting. Awesome. John's got a question for Sasha again for MRV. Would it work to measure the amount of magnesium reacted instead of trying to measure carbonate created? And he's thinking about new or unique ways to do MRV, potentially for lower costs.
Sure, I'm not an expert up to date on how that's being implemented in field trials. I think Amanda Stubbs might be, though, where people are trying to look at cation and anion balances. Typically, for simplicity, we tend to just measure the carbon, since it's a more direct measurement of what's stored. But I know there are new MRV techniques that are under development.
Yeah, I can mention one kind of something that's I think more commonly done now over the past couple of years is what you're right that you can measure not necessarily the magnesium itself, but the absence of magnesium. So when you amend this rock that's magnesium rich, as you weather it, that ideally that magnesium and the calcium are percolating through as alkalinity and through the rainwater that comes through, and what people will often do is they will take, you have your initial magnesium level, you have your measured magnesium level throughout the trial, and then they'll compare it to a non-mobile element, often like titanium, for example. And so as you see your magnesium deplete, as long as your titanium isn't also depleting, what it generally means is you're getting this weathering as opposed to a physical transport. Whereas if you see both move, then it's much more likely that it's a physical transport. If that makes sense.
Yeah, sounds good. That's all we have in the chat right now. There's some questions that folks submitted when they registered. So I've got a couple of those here. Maybe at like a higher level, or taking a step back from this specific analysis, can you give a sense of how much more removal enhanced rock weathering does on top of the natural weathering process? And I don't know if that's like a sense of scale, or just give us an idea of how much more removal we're actually creating through this method.
Yeah, I'm not sure if anyone's I'm sure people have tried to quantify that, but it's orders of magnitude just because of your increase in surface area is so vast that the rates at which you're weathering go from thousands of years to ideally a few ones to tens of years in unfortunate circumstances if you go higher than that. But it is generally orders of magnitude multiple quicker than natural weathering.
Just to build briefly on that, if I may, estimates for how much CO2 is naturally sequestered by rock weathering, it's about 500 million to a billion tons a year. But folks who've done estimates for deployment in agriculture are, like Jonathan said, looking at multiple gigatons per year. So it would dwarf the natural carbon cycle if conditions were good and CO2 sequestration was optimal.
Awesome, thanks. Maybe Jonathan, from the results of the model, then, if we think about Canada specifically, are there certain opportunities you'd highlight that seem, interesting or worthwhile to pursue a little deeper? I'm thinking specific regions paired with a certain type of rock, like one of the 4 rocks you looked at, or anything to highlight for Canada specifically from that geographic mapping.
Yeah, I mean, I think the ideal scenarios are going to be areas that have relatively low electricity emissions. So, unfortunately, that eliminates most of the prairies from that perspective. But again, if you can transport it via train, it's still certainly feasible in the prairies. It's still low cost. I'd say actually what's not considered in the model is likely a larger factor on the CDR rate as well is going to be the precipitation rates, temperatures, and kind of soil conditions. And so BC is ideal looking at all these components. It has a lot of basalt. It has a lot of these potential mines. It has it has higher temperatures than the rest of Canada. It has higher precipitation rates. Ontario and Quebec are good. They have a lot of mines. They have a lot of agriculture. They have higher temperatures than the prairies. They have more efficient electricity grids. So I think generally that's going to be where you're going to want to look is areas that have slightly higher precipitation rates and temperatures as well as more efficient grids. And so, yeah, I mean, Quebec, Ontario, BC are probably where you're going to want to start looking. But I know there are already relatively large scale deployments going on in Ontario, actually. So it's being done in practice.
Cool. And then question just came in from Allison. Within your results, can you elaborate a bit more on that carbon price analysis you did and how you're relating that to the pricing you found, and also what does feasible accessible farmland mean? And if you want me to pull up a slide, I can do that too.
Sure. I mean, I don't. We can go look at the carbon price slide. Essentially, all that's done in that slide is just comparing the total cost per ton CDR to the cost of carbon in a given jurisdiction. So if a given province, state, or country has a carbon price that's higher than the cost to deploy to any given hectare of farmland, then that's considered in that number. So the 12,891,000 number, for Canada there is saying that under our worst case of the 6 scenarios we looked at, you can still get 12,891,000 hectares of deployment for costs per ton CDR below the industrial carbon price. So that's what that metric is looking at. And so that's why Canada has obviously the highest amount of that feasibility. And that's just because of our higher carbon price and lower costs to deploy. And so what was the second component? What does accessible, feasible
What does
farmland
feasible or accessible farmland mean?
Well, I guess in the case of this study, it's essentially feasible is just the lowest cost possible. And so feasible from a carbon price perspective would be below the current carbon price. But yeah, feasibility is going to increase for deployment with decreasing costs. It's unfortunately just how it has to be. The investment is more useful in areas where you can deploy to, at lower costs. So.
I'll pause for a second to see if any last questions trickle in. If not, okay. Oh, Francisco's asking, based on this work that you've done, yeah, a summary of the top 3 things driving cost per ton captured with enhanced rock weathering. I think, it's maybe covered in a couple others, but to wrap it all up, what are the top impacts?
So it's going to be number 1, CDR potential of the rock, right? So how much carbon can I actually sequester from a given ton of rock? That's number 1. Number 2 is going to be proximity to low cost, low emission transport, so trains or shipping. And then, for an actual cost perspective, number 3 is probably the input energy costs at the mine site. So if that'll be if we're using grid electricity, low grid emissions, low grid energy costs. If we're using solar, again, accessibility to solar. And then unfortunately, diesel is it's going to be, if we're using diesel generators, it's going to significantly reduce the efficiency regardless, because there's no way to avoid the emissions there. But yeah, mainly energy cost, transport, or I guess proximity to low cost transport, and then CDR potential of the rock itself.
Great, thank you. All right, I think question-wise, sorry, we got time for one more. Let's see.
There's a good question from Ellen, it looks like. Just put it in the chat.
Any info available on public perception of enhanced rock weathering in Canada or the United States? Yeah, do you want to take that?
A good place to plug, I think, other CanCore members, where we have actually a dedicated social scientist looking at doing actual surveys and kind of laying out the benefits and potential side effects of different CDR techniques. And so that, I don't think anything's publicly available yet, but there's a lot of work going in towards assessing public perception. I will say what I do know is generally Ontarian farmers seem to be more receptive to this. I think that's the only area I know with particularly large deployments going on is Ontario. And I think that largely is due to the work that companies and researchers out east are doing with farmers, as well as the fact that wollastonite, which is one of the potential rock types to use for ERW, has actually been used before considering its carbon removal potential. It was actually used as a pH amendment for decades in Ontario already. So that obviously makes it a little more palatable when you know the rock already.
Yeah, for sure. Helen, Jonathan's referring to Melanie Thomas from the University of Calgary, who's doing a lot of this public perception work through surveys, and so you'll just have to tune in next year for another webinar, and we'll have some of those results, I'm sure. We'll close it out here. Thank you so much, Jonathan and Sasha, for a great walkthrough of the process and some of the analysis. We'll have your contact info. It's on the website at cancore.ca if folks want to reach out. And I am going to plug here our next webinar in the series. So that's happening November 13th, a couple months from now. It is called Moving Beyond Carbon Accounting, Understanding the Full Climate Impacts of CDR, featuring Kirsten Zickfeld, Distinguished Professor of Climate Science at Simon Fraser University, and Isabel Dove, a postdoc fellow with Kirsten at SFU. And so this will be a fascinating one that looks at other impacts that CDR has to our climate outside of just carbon. And so you'll definitely want to tune into that. Margaret's dropped the link to register in the chat there, and you'll see us on social media start to talk about that next in the coming weeks here. Thank you so much. Thanks again, Sasha and Jonathan. That was great. Thanks for everyone who chimed in with questions and came in to join the discussion. And I will abruptly end the webinar here. Take care, everyone. Have a great day.
Thanks, Carson.